All right, so in this section, I want to talk a little bit more about the theorem we just proved, which was that bounded monotonic sequences converge, okay? Because it's actually, the theorem might be a little bit more powerful than you might realize at first. Because, I want to sort of point out a key feature of the theorem that you might not have it might not have stood out to you at first, but this is really where the power of the theorem comes from, okay? So the thing is, in theorem 10.2, we didn't know the value of limit of Sn. I mean, we sort of knew it, right? We didn't know, quote unquote, right? Obviously, in the end, we decided that the limit had to be the supremum, at least for the increasing sequences, right? The limit was the supremum of the values, okay? But that's sort of it's kind of an impractical description of the value of the limit when it comes to computing values of limits of sequences, right? That's not really a useful thing to say. Oh, it's the supremum, right? I mean, so what is that? Like, proving what value that has is probably just as hard as proving that the sequence itself converges to that specific value anyway. So, so the fact that we didn't know it in the proof came from the fact that in the statement of the theorem is very general, that you don't know anything about Sn itself, right? We didn't know much about Sn, right? But this means that the theorem can be used to show sequences converge even when you don't know their limits. Okay, that's the true power of the theorem, is that you can apply the theorem to sequences that are very hard to compute, whose limits you can't really describe. Okay, and in fact, a famous example of this would be, a famous example of this would just be, I'll just say one can show that 1 plus 1 over n to the n is monotone, monotonically increasing, and bounded above by 3, okay? And of course, this sequence, as you might remember or might know, is commonly used to define the value of E. The limit of this sequence is actually E. And the thing about it is, like, you can't just show this converges to E, at least unless you've defined E in a totally different way beforehand. Because if you're taking this to be the definition of the number E, then, how can you use anything about E before you even know that this sequence converges, right? So there's sort of a little bit of a chicken and egg problem here, and it's solved by just not even worrying about what the value of the limit is, and showing this in this kind of rough-handed way, showing that the sequence increases and that it's just bounded above by any number at all. That tells you that it has to converge to something, and then you can say the limit of the sequence, whatever that may be, we're going to call that the number E, right? So that's kind of a famous example. Another example is one that they give in the book, which has to do with recursively defined sequences. So in the book, they use this example of a sequence defined by the following rule. So e.g., S1 is 5, and Sn plus 1 equals Sn squared. Oh, they write it slightly differently, but whatever. Plus 5 over 2Sn for n greater than or equal to 1. Okay, so this using this rule, once you know the first value, using this rule allows you to get the next value, and then you can use that value plus this rule to get the third value, and so on, right? So all the values are defined, but the expression for the nth value gets more and more complicated. And in fact, off the top of my head, I'm not sure what the formula would be, just from looking at this, what the formula for Sn in terms of n would be. But the good news is that using Theorem 10.2, you don't even have to write down a formula to be able to argue that this sequence converges. You can show that, show by induction that Sn plus 1 is less than or equal to Sn. So it's a decreasing sequence, and clearly Sn is greater than 0 for all n, so it's bounded below. So then by theorem 10.2, Sn converges. And of course, some of you also might know the trick for like actually figuring out what the value of the limit is, and that is, you know, setting up an equation where you'd write something like L equals L squared plus 5 over 2L or something. That would be, then if you solve that equation, L would be the limit, or at least you'd get a number of solutions, and one of the solutions of this equation would be the limit of this sequence. So the limit has to be what's called a stable point of the iteration or whatever. But I don't want to get too bogged down with that, right? Why that's the case right now. And I'm not going to go into this proof. You can find it in the book. I think it's kind of interesting and it's fun to see. But these just kind of illustrate the power of theorem 10.2. So you can do a lot with sequences if you know they're monotonic, even if you don't really know anything else about them. In the next video, I'll talk about unbounded monotonic sequences because they still exhibit sort of very specific behavior.